Thanks. Thank you for that lovely introduction. So my name is Rúnar. I'm one of the founders of Unison Computing. Our mission is to advance what is possible with programming languages and to make modern software development more delightful and more accessible. We are a public benefit corporation, and that means that we're focused on this mission above anything else. And so to that end, we made a programming language called Unison, which I like to say is a friendly language from the future. And we made a cloud computing platform called Unison Cloud, which is mostly written in Unison. And it runs, you can use it to deploy and run resilient, scalable Unison program and services. So my goal is to tell you about Unison and to get you curious enough about it to go and try it out. And then obviously you're going to write all of your software in Unison from then on. But I can't tell you everything today, so I'm going to tell you about it through the lens of developing systems that use microservices or microservice architecture. So microservice architecture give you some big benefits, but traditionally you also sign up for a world of pain when you go to microservice architecture. And Unison mostly makes those pains go away, and I'm going to show you how. Okay, so what is Unison Cloud? Well, Unison, first of all, Unison is a purely functional, statically typed programming language. And it's open source, and we have a growing and friendly community at unison-lang.org. And then Unison Cloud is a distributed computing platform that you can run your distributed, resilient Unison programs, workflows, and services. And that is we're hosting that on unison.cloud, so you sign up for a small monthly fee to run your programs. There's also a free tier for playing around. It runs on top of AWS. You can also run on other cloud providers. You can run it on your own hardware, or we can host a virtual private cloud for you, or whatever. It's very flexible. But the big idea with Unison is that a Unison program can talk about what an entire distributed system is doing. And so distributed systems can be ordinary typed composable libraries. And you get all the benefits of a programming language when you're writing these distributed systems. Okay, so microservices. Why do people use microservices? Well, there are some really compelling reasons for designing your systems in this way. So first of all, you get these sort of system benefits. You get independent deployment, scalability, and fault isolation. So you can deploy individual services regardless of the rest of the system, and you can scale parts of your system up and down without having to scale your whole system. And then if some of your services go down, the rest of the services can stay up, and they can continue working and fail gracefully. And then you get these team benefits. Teams can be more agile and more autonomous. You can iterate quickly on these small units, the microservices. They're easier to test and debug because they're small and isolated. And teams can make, this kind of architecture enables, if you were in a Joachim's session yesterday about Spotify, it enables this team autonomy that a team can be in charge of a set of microservices and then make decisions all the way up the organization about those services. Okay, so really good reasons to do that. But also, you sign up for all of this complexity. Like the microservice architecture is traditionally not really feasible below a certain size of organization. Like you need a lot of engineers, maybe, to manage the complexity that you get with deployment and orchestration. And so on the slide here, I have a picture of the Uber microservice architecture. This is from maybe 6 years ago. I got this from their blog. And every one of the dots in this graph is a microservice. And the lines between them, the gray lines on the slide, are service boundaries. And so every time one of these services is calling another service, that adds latency to the system. But also, some poor programmer has to write like a custom protocol, has to generate some code or like a JSON protocol or something to specify like what that interaction looks like. All right, so that's a lot of work. But also, the protocol might be changing over time because these services are changing, and so versioning of the protocols is an ongoing concern. So you need more people for that. And then the refactoring can be risky. Like I find that once you've deployed a microservice, it can be difficult to get rid of it. Or it can be very difficult to move where the boundary between microservices lie, like to change the responsibilities of a microservice. And if you've worked on a system built with microservice architecture, you will know that much of the work in building the systems is not coding. It's not like writing the business logic. It's a lot of stuff like managing the build and writing the deployments and writing all of that service boundary boilerplate. And then there's all this sort of meta infrastructure, which is like writing services that their only job is to know where other services are running, or like writing configuration and managing the deployment of like tools that you use to manage all of this complexity. Okay, and programmers hate this. I know I hate it, and I just don't want to do it. Like I want to read one of these comments to you here. This is Rob Norris. He's a Scala programmer. He says, "I still find it mind-blowing that we have this skyrocketing tower of technologies and an entire new profession dedicated specifically to figuring out how to run stuff on AWS. What on earth is going on?" Yeah, so okay, what on earth is going on? Why is so much of this work not programming? Why is there so much stuff besides writing the business logic? Well, I think that it's mainly due to the simple fact that currently what we consider a program is really just talking about what a single OS process is doing on one computer. Okay, but there's so much other stuff that has to be specified in a microservice architecture. Because when you think about it, the code is really just the stuff that's living in these little dots. Okay, but how those dots get there, and then how the lines between them are established, and what exactly those lines represent, that's all specified using not code. You could say that like YAML files and protobufs and JSON schemas and whatever are code in a way, but you certainly don't get to do it in your nice programming language with types and autocompletion and stuff like that. Because programming a single computer like this, back in the era of shrink-wrap software, it was a super nice experience. You write a program that runs on one computer, and all of your questions that come up while you're writing the software are programming questions. They're questions like, oh, how do I sort this list? Or, like, how do I call this library? Or this OS call, or whatever. And the answer is always, or usually, well, I'm going to write an elegant function in a purely functional programming language. I'm going to use types. It's going to be sunshine and rainbows. It's amazing. But when you move to writing programs that need to run on a lot of computers, the questions that come up are not just sort of bigger in scope, but they're totally different. So there you are, like you haven't written code in a week, right? And you're like, okay, so how do I add an auto-scaling group to my managed Kubernetes cluster? And well, you can't talk about that in a programming language. So you have to reach for advanced technology, like the Kubernetes autoscaler YAML file. And you're sitting there reading some kind soul's explanation of all this unguessable nonsense, and you're thinking like, well, what am I doing with my life? I thought I was a programmer, but here I am, reading this stuff. And the reason I think that this stuff is so hard, and the reason for most of the problems with like microservice architecture and distributed systems maybe in general, is that programming is trapped inside of this little box. It's trapped in the single OS process on one computer. And so Unison liberates programming from that box and sets it free. And so like I said, a program in Unison can talk about what a whole distributed computation is doing. And therefore there is no need for builds or containers. There's no build in Unison. You deploy your service by passing it to a function. And you call another service with one line of code by calling a function. There is no bespoke serialization protocol. There's no code generation to make that call. Services are strongly and statically typed in the language. So you pass them ordinary typed Unison values, or sort of plain old Unison objects. And you get back typed values that you don't have to parse. They're just values in the language. And then storage, persistent data has this same character. So working with storage or persistent data in Unison is a lot like working with in-memory data. And you end up having things like distributed hash tables as a data type that you can just work with as if it were a normal data type. All right, that's a lot, but I want to talk about the first one of these. So no builds and no containers. How is it that Unison does not have builds? So first of all, what is a build? With a traditional programming language, the build, besides maybe compiling the code if you're in a compiled language, the build ensures that all the code can address its dependencies. So it makes sure that each library dependency has a specific location that is known at runtime, and that it is of a specific version that is definitely compatible with our code and also definitely compatible with all the other dependencies. And then the build creates a reproducible artifact. We give it a name, usually a unique name, and this is going to be like a Docker container or a jar file or a set of jar files or whatever. And then we refer to this artifact uniquely by that name, like if we want to roll back or track bugs or something. And then usually also the build will run all the tests on our code and regressions and stuff, catch bugs. And typically, it'll run all the tests even on code that hasn't changed since we last did the build. But Unison does not need to do any of this stuff. And the reason why, and I want you to listen closely here because this is Unison's one simple trick. Every Unison definition has a unique and deterministic identifier, or name, or address, which is a hash of its implementation. Okay? And the hash identifies the exact version of the function, including its entire dependency chain. So it's determined by the implementation of the function and the implementations of its dependencies, and so on. And so Unison has no builds because, well, dependency resolution is baked in. Every dependency in Unison is identified by its hash, uniquely and deterministically. There's no need to resolve like dependency paths or dependency versions. Every function always references exactly the code that it needs. And this is a topic for a whole other talk, but code in Unison is an immutable data structure instead of being a bag of text files. And so once a function or type's hash is created, its implementation is fixed forever in the code base. Okay, this eliminates the possibility of any runtime surprises, like due to dependencies changing on you. Deployment is by hash. So deployment in Unison is done by passing a hash to an ordinary Unison function. And then when you deploy, the remote location receives exactly the code that you want because you're passing it the hash. And then since every function and dependency is identified by its hash, you get consistency across environments. There's no like works on my machine issues. If you're familiar with Nix, this is very much the same idea, except Unison's granularity is much higher. So the hashes are on the individual functions and types rather than at the package level. And then, so with tests, you only run tests on hashes that have changed. So tests have hashes as well. And so if the stuff that you're testing hasn't changed, there's no reason to run the test again. You run the tests as you write the code. Once you've written the code, you've saved it to your code base. You run the test, and it's run forever. You don't have to run that test ever again. In fact, nobody has to run that test ever again. Okay, so what about this next one? Deploying with a function call. Yes, so in Unison, you deploy with a function call. And it really is like this. This is real Unison code that deploys a real service. Well, I just called it my service, but this is what it looks like. And deploy here is an ordinary function. And MyService is the function that implements the service. So deploy here is a higher order function. It takes a function as its argument, as its second argument. As the first argument, it takes the environment in which you want to deploy. And the environment is stuff like configuration and secrets and access controls and stuff like that. Okay, so a number of questions will come up for any language to do this. If you want to deploy with a function call in any language, you have to answer some questions. Questions like, how do we send the code? And what about the dependencies of my service? And what about dependency conflicts? And lastly, so my service could be a closure. Like it could have been constructed by passing it, say, a file handle, and then it proceeds to read that file handle or write to it or something. And that could be dangerous. So how do we ensure it doesn't do that? So the first three of these we solve by everything in Unison being serializable, including functions. So everything in Unison, serializable. All dependencies are known at runtime. They are generated at compile time. So when you compile your Unison code, it generates a list of all of the transitive dependencies of the hash. And so we know the full list of transitive dependencies at runtime of everything, of every hash. And then dependency conflicts aren't possible because the dependencies are encoded in the hash. Okay? And then this last one, we'll get to it in a bit. But the thing is, we verify the absence of file operations, file I/O operations statically. We'll get to that in a minute. So I want to give you an example. Say we want to deploy this function as a service. So this is a simple text summarization service. It calls out to ChatGPT. It uses the OpenAI library, which is a Unison library. And this is real Unison code for a service. I wanted to show you something that actually does something. But first, I want to draw your attention to the type. So it is of type text to text. So summarize takes a value called input, which is of type text, which is Unison's way of saying string. We just think it's a more friendly name than string. And it returns some text, which is a summary of the original text. And then the stuff in curly braces is the sort of context in which it can run. So these are the effects that it can have. So this function, summarize, wants to read the API key for OpenAI from its configuration. It wants to be able to throw exceptions, and it wants to use HTTP to call out to OpenAI. And so it just goes in and manipulates the OpenAI API through that library by calling that chat completion function and saying, I want GPT-4o mini and give it the prompt. Okay, so the question is, how do we serialize this function? So in a language like JavaScript or Python, you could do this by using some kind of reflection or something. You can somehow get the structure of this code and then send it to the remote location. But you'll run into issues because it has references to other functions. And also, there are functions in here, so you need to be able to serialize functions in general. But this chat completion thing here is a reference to a library. So then what do? Do you serialize that whole library? Do you, what does chat completion mean at the remote location? So maybe chat completion has moved on. Maybe there's a completely new version of the OpenAI library, and it it's a different type. And so you're going to get a runtime error when you try to call this. But Unison solves this by just referencing the function by hash. So internally, instead of the code having the name like chat completion, like OpenAI.chatCompletion or whatever, it just has this 512-bit identifier in it, which is a hash of the implementation of the function that's being referenced. So I'm only showing the first few bytes of the hash because they won't fit in the slide. But so we're using Unison's sort of one simple trick here. Okay? So Unison code will have has a canonical binary representation, and references are always just encoded using the hash. So then what happens when you deploy a service is that at compile time, we generate the full list of transitive dependencies, which is associated with the code. So this is a list of hashes. And then at runtime, deploy will serialize the code. It will send the serialized code to Unison Cloud servers. And Unison Cloud will come back and say, well, you sent me the list of transitive dependencies. There are 4 hashes here that I don't recognize. Please send me the code for those. And then it sends that. The client will send that. And then we put that at an endpoint that you can then call. OK? So we've seen how Unison solves the first 3 of these questions, like how to send the code and what about dependencies. But this last one, like how do we make sure my service doesn't do something dangerous or something that's actually impossible at the remote location? And the answer to that is types. So here is the type of the cloud deploy function that we're calling to deploy our service. And the way to read this is that this is a function. It takes 2 arguments. It takes an environment, first of all, that we're going to deploy to. And the second thing is a function. It's a function from some type A to some other type B. And then it has a list of effects that it is allowed to have. At the bottom, you can see that the whole deploy function returns a service hash. So it's a hash of the service, a service that takes an A and returns a B. So it's a service hash is typed according to the calling convention. And the deploy function can throw exceptions, and it talks to Unison Cloud. But the function that you pass to it, the thing that actually implements your service, is allowed to read its configuration. It's allowed to throw exceptions and talk to durable storage and do HTTP requests, generate random numbers and fork off remote processes and stuff. But it is not allowed to do I/O. Right? That is not in the list. And so if you try to close over a file handle and read from it, you will just get a type error at compile time. So that's how we solve that. So the upshot of this is that Unison Cloud services are statically and strongly typed. And so to call them, you're not going to be sending them like untyped blobs of JSON or whatever, unless that is actually the type that you want to pass to it. But you're going to be passing values of the required type that is specified in the type signature. OK, so how do we call a service? Well, we call a service with 1 line of code like this. Services.call is a function in the Unison Cloud client. So you get that in the Unison Cloud library. And it's just 1 line of code. Right? You pass the hash to services.call, and then you pass your argument. And you'll note that there's no serialization boilerplate or anything like that here. No, we're just sending text here, so maybe that's not that cool. But you could be sending an arbitrarily typed, like complex data type here over the network here, including functions. You could send a function to services.call and pass a function to your service. So that would be totally fine. So here we're calling the service by hash, but somebody changes the implementation of the service that you're going to call, and now it gets a new hash. And so now you need to change your code. And that's no good. So we have this notion of a stable name. So you can say service name.named, and that will idempotently create that name. And then we say service name.assign, and we assign the name to the hash. And then you ship the name around, like to people who want to call you. They get this nice typed name in a library that they import. And then they use services.callName to call the service by name. And so then you can assign the name to a new hash, and your callers will be calling the most recent hash that's deployed. OK? So then what happens when you call a service? Well, we can imagine that when you call a service, we serialize the argument, including the variables it closes over. We send the list of transitive dependencies, all the hashes, and then any required hashes that are not already on the server, it will request. And so basically the same as when we deploy. But this is not what happens. If there is headroom on the calling node, Unison Cloud will actually dynamically deploy the service that's being called onto the caller. Right, so we just do sort of a deployment in reverse. And so the two services are going to be co-located on the calling node. And while they're co-located like this, no serialization needs to take place, and there's no network boundary at all. The service that is making the call is really just making a library call into the sort of reverse deployed service. And we call this adaptive service graph compression. And we can do this for the same reason that we can deploy with a function call. We're just deploying, in reverse. So Unison is, in a way, kind of just in time compiling your service graph to a monolith at runtime. Now, other than eliminating network hops, one of the cool outcomes of adaptive service graph compression is that you don't really need to write like batching versions of your endpoints. So you will have, typically, you'll have a service that like takes one text that you want to summarize, and there's another one that takes like a whole batch of text you want to summarize to eliminate that sort of network hop. But in Unison, since we're actually deploying the service on the caller, you can just call it in a loop, and it'll be fine. So this will, this will induce at most one network hop, which is the network hop to actually, ask to have the service deployed. But if it's already deployed, like if we have called this service before, it will already be here, and so there'll be no network hops here at all. There is a small amount of context switching overhead here in this services.callName function, but it's not going to be anything compared to a network call. Also, if nothing calls your service for a while, it's going to get automatically garbage collected by Unison Cloud. And what this means is basically it's not going to be in memory anymore on any node, but it's still going to be present sort of in long-term storage. And Unison Cloud will load it again if it's ever called. But so we have automatic lifecycle management of your services. And so programmers don't have to do that themselves, which I think is awesome. All right. Now I wanted to show you a little demo if the Wi-Fi gods allow it. But first, I do want to highlight some of the things in the code that I'm going to be showing. So the code I wanted to show you I wanted to show you something useful. I wanted to show you something that like actually does something. And I was thinking like, okay, what is a demo or something that we can write fairly easily, but also actually does something and is kind of a canonical example. And I thought, well, currency converter, right? So the thing I'm going to show you is an enterprise currency converter, which when deployed, it will like scale up and down in response to load. So like if your currency converter goes viral on Reddit or something, you can handle that. And also like, parts of it can go down or whatever, and it's going to be fine. Okay, so the first thing I want to highlight is this notion of cloud daemons. So sometimes you want to deploy just sort of like a workflow or some code that you want to run either continuously or periodically. So it's not a service that you want to call. And here I have a daemon called job. And all it does is call this refresh rates function, and then it goes to sleep for 24 hours. And the code below it is the deployment for that function. So that's the thing that actually deploys it to Unison Cloud. And the refresh rates function, I wanted to show you here that this is using typed durable storage. So this is actually using a relational table. So it's called an ordered table in Unison Cloud. And so I'm saying this named thing, it's table.named, but we don't actually have to say that here for reasons that I'm not going to get into. But this exchange rates table, we're going to write to it using that write.tx thing. So I'm just saying for each rates that I get back from the European Central Bank, I'm going to make an HTTP call to the European Central Bank, and for each exchange rate that I get back, I'm going to write it to the rates table. And you'll know that there's no like serialization stuff going on here. There's no like type mapping or anything, okay? And we're doing this in a transaction. So all of these rows are going to be written as a single transaction to this table. And then on the other side, this is the currency exchange service. So it takes a database, so like where is the data? And then it takes a triple, which is the stuff that the client is going to send us. And so it takes two texts, which are the names of the currencies that we want to convert between, and a float, which is the amount. And then it returns a float sort of in this remote context. Okay, and then what it's going to do is talk to the database. So, if the currency is euros, then all the stuff is denominated in euros because it's the European Central Bank, then it's 1.0. Otherwise, we're going to read the exchange rate from the table, and it's just as simple as saying read table currency. There's nothing else you need to do here, and then we do the calculation. Great, so this is our service. This is our enterprise exchange rate service. Okay, so now let's see if the Wi-Fi will cooperate. All right, so here I'm working in Unison. So this is the Unison Codebase Manager running on the left. This is what you run. Generally, you keep this open. This talks to your editor, and it also allows you to type in commands here to see what is in your code base, and allows you to view docs, and you type commands to modify your code base, which is an immutable data structure. Okay, so I can, for instance, type ls here to see what's in here. I have nothing in here except lib, which contains my dependencies. But over here, I just have VS Code, and this is all the code for this service, the exchange rate service. And I have this type, which is the stuff that I'm going to get back from the central bank. I have a JSON decoder, which, because we're going to get JSON back, so I decode that into my type. Here is the exchange rates service that I showed you on the slide. And then this is the daemon I also showed you. And this is the implementation of the refresh rates. It's doing a little bit more to support UI, so it's also getting the names of all of the currencies in addition to getting the exchange rates. But this is basically what you saw on the slide. And then here's the deployment for the exchange rate service. This is the deployment for my edge service. So this is an HTTP server that calls out to my service. You can see here at services.call, I'm calling the currency converter when I receive a get or a post on a particular endpoint. Okay? And then here I have a thing called deploy everything, which will deploy the daemon. It will deploy the exchange rate service, the edge service, and the user interface. And this is the user interface here. It's an HTML page. It's written in HTMX, using the HTMX library in Unison. Okay, so that's basically all of it. So now I'm going to see if I can run it. So it's not running right now on Unison Cloud. So as I say run, deploy everything. Did I get it? No. Yes. Oh, I need to actually save this file. Okay. So now I have saved this file, and the Unison Codebase Manager says, like, okay, here's a bunch of stuff I found in your file. And then I can say add, to add that to my code base. Say, okay, here's all the stuff I added. Great. So it's really in here now. And actually, I can go and delete everything that's in here. We don't need this anymore. Because the way you work with Unison generally is that you're just kind of modifying this code base. And your text editor is more of a scratch space than anything else. Like I can get back, refresh, right? It's by saying edit. Whoop, I think I forgot to save this file. Is it in here? It's not. It says I added 0 definition. What's going on? Refresh rates. 13? 0 definitions. I actually don't know what's happening here. Okay. Can I do deploy everything? No. There's some, so maybe I probably need to restart VS Code, which is what's happening here. But anyway, so I've added that. So now let's say I can run deploy everything. Okay. And now if the Wi-Fi cooperates, we should be deploying this to Unison Cloud right now. The Wi-Fi here is not fast. But okay, it's done something. Deployed one of the services. deployed my edge service. Okay, and here is the UI. So if we go to visit it, it showed up in the other screen. So here it is. Sweet. We have our UI here, and obviously it defaults to Australian dollars. I mean, that's just correct. And we're going to convert from Icelandic krona to to Australian dollars. And yeah, 100 ISK is 1.12 something Australian dollars as of today. So this is, it's an enterprise currency converter that scales up and down, and it is super resilient and stuff. And you can show this to all your friends, and they can share it around, and your stuff will not go down even if it goes viral, right? Okay, so that's the end of that demo. And now, I had some backup, in case the Wi-Fi didn't work. Okay, so developers love working on Unison. And I think you will too. And so here are some things people are saying. Things like, well, I'm completely awestruck. Or, it brings back the joy of programming. Leaps and bounds beyond the usual serverless approach. And our own Chris Jenkins, I don't know if Chris is here today now. If you watched Chris Jenkins' talk yesterday. But Chris Jenkins says, just next level brilliant. And my favorite one is the Hacker News user, and he says, to be honest, this is not the worst idea I've seen. Which, if you know Hacker News, that is high praise. All right, so in summary, microservices can be easy and fun, and they're within the realm of possibility, even for teams with just one engineer, if that engineer is using Unison. So I want you to give Unison a go. And come talk to me at the conference, or we have plenty of time for questions if you have any. So thank you.